Okay, kiddos, here goes a description of answers to our practice quiz for projectile motion from AP Physics. First question, a boy runs and jumps horizontally off a dock 5/4 of a meter above the water. So these questions are actually designed to be done without a calculator. The numbers end up sort of working out simply, and if you're doing that, just use 10 instead of 9.8 for the acceleration due to gravity, and watch what happens. So his velocity at the end of the dock is most closely, all right, so we know this is the distance that he falls, and this is the horizontal distance that he goes, and we want to know the horizontal velocity. So if we were plugging into the 1/2 AT squared formula, we know the distance fallen would be 1/2 A, so 1/2 of G, which if we were using 10 for the acceleration due to gravity, half of that is 5, and then T squared. And we know that in the horizontal direction, in the vertical direction, the initial velocity would be 0, and we can say that the initial position is 0. So solving for this, I'd put a negative there because we know that if the initial position is 0 at the dock, then below the dock that would be a negative 5/4 right there. So the negatives cancel out, the 5s cancel out, and we have that t would be equal to the square root of 1/4, which is 1/2. So it takes him half a second to fall. So if he goes 2 meters horizontally in half a second, how far would he go in 1 full second? And the answer is 4 meters. So his horizontal speed would be 4 meters per second. If you were actually using a formula for horizontal direction, it would just be that distance equals velocity times time. So we could say x equals velocity times time. Again, acceleration in horizontal direction for projectile motion is 0. 2. A projectile explodes at the top of its arc. So its arc, it explodes. The first piece stops from the explosion and falls straight to the ground. If the projectile had not exploded in flight, it would have landed 1 kilometer away. The second piece lands, and where is this? So, explodes at the top of the start, splitting into 2 equal pieces. So we have some projectile. It goes like this, and then right here, boom, it explodes, and part of it falls straight down, and part of it's going to go someplace else. So the path it would have taken is like this. And it says if the projectile had not exploded in flight, it would have landed 1 kilometer away, meaning this distance is 1 kilometer. So this question is kind of related to like conservation of momentum, which we will get to later. But I thought you could sort of intuit your way through it, where if half goes this way, then the other half is going to go twice as far as it would have. So it's like this, like this. So we could say that the center of mass of these two, or the average of these two, would land where the projectile would have landed. So the second piece lands, and this would be 1.5 kilometers away. 3, this is related to that monkey and gun video that you watched, where the bullet falls at the same rate that the monkey does, or the dart, and the dart hits the monkey. So, same situation, we have a gun that is being fired horizontally, and it would go perfectly straight if gravity weren't pulling on it, and here's the person in the tree. And so what happens is the person rolls off the tree right as the gun is fired, and the person will fall at the same rate as the bullet, surprising as that is. So the bullet will hit the soldier unless he is too close to the ground, meaning if the soldier were very close to the ground, he would hit while the bullet is still in flight. So the bullet would hit the ground over here, and the soldier would hit the ground over here. Question 4, projectile is fired upward at 90 degrees, so like this. A similar projectile is fired at the same velocity at 60 degrees, so like this. So I did a little right triangle trigonometry. I knew that this would be 1/2. Hey. So I did a little right triangle trigonometry, and I got 1/2 and √3/2 and 1. The height attained by the second projectile is what fraction of the height of the first projectile? So we're looking for height attained as a function of initial vertical velocity. So the height attained, this is from our 1/2 at squared formula. Let me try to write it out, see what happens. So height attained, we have our initial position, which would just be 0. We have our initial velocity times time plus 1/2 at squared. Right. So the height attained depends on initial velocity, but it also depends on time to maximum height, which in turn depends on the initial velocity. So if we were taking v sub y over g and substituting it in for t, let's see what happens here. We would get our height depending on our initial velocity in the y direction times initial velocity in the y direction over g, and 1/2 a, which is always going to be constant, and then t squared. So this is v sub y over g squared. So what it looks like, you see how we have velocity in the y direction squared and velocity in the y direction squared. So height attained is proportional to the square of the vertical velocity. I'll say that once more. The height attained is going to be proportional to the square of the initial vertical velocity. So, in the angled projectile, the initial vertical velocity is this fraction of 1, and so if we square that, we get this. So the height attained by the angled projectile will be 3/4 the height attained by the projectile fired straight up. 1 squared is 1, √3/2 squared is 3/4. Tough stuff there. Question 5, a stunt flyer, so we need this graph. A stunt flyer in a small airplane is attempting to land in the back of a truck. Positions are shown in the above graph. So we have truck and we have plane. This is position versus time. So the truck looks like, if we were to sort of calculate the slope, it looks like it's going about twice as fast, as the plane, which doesn't make a lot of sense, but that's what's going on. Assuming the velocity of the truck does not change, meaning the slope does not change, in order to land on the small truck and not crash, the plane must. So the plane is going to have to catch up to the truck, first of all. Okay, it's going to have to increase its rate of change of position with respect to time. It's going to have to increase its velocity, speed up to catch up with the truck. And then, so if we were to continue this, let's say the plane would go something like this and speed up, and then to avoid crashing, it doesn't just hit the truck, but it slows down. So right as it comes into the bed of the truck, this would be quite the stunt. The plane would not crash, but would just land right here. Okay, so it would have to sort of at that point be going the same speed, meaning it would have to accelerate and then decelerate, so speed up and then slow down. So speed up and slow down. Question 6. All right, so it's tempting to just say both of these work, but that's not really the case. To help you think about this, I sort of recommend not looking at the graphs and saying a bungee jumper jumps from a bridge down into a deep ravine. Her position and velocity. So if we were drawing position versus time, position versus, time, right as she jumps off the bridge, she's actually going slowly and then speeds up and speeds up and speeds up in the negative direction. So let's say we're saying that the height of 0 is right on the bridge. As she falls, it would look like this. And then if the bungee were really taut bungee, and she'd probably get injured doing this, but she'd immediately sort of boing up like this, and it would look something like that, like a bouncing ball, okay? But the bungee is probably not that taut because hopefully she doesn't get injured. So it would be kind of like that, but, kind of like that, but less extreme. So like, let's take that and make it less extreme, meaning sort of smooth out the curves, okay? So it'd be kind of like this, kind of like this. So this is close, but in this she starts out moving as fast as possible, which is not correct. So if we took this graph and we were to draw the velocity versus time graph, so I think we've done one like this in class where we had a position time graph like this, and the velocity time graph is, 0 and then goes in the negative direction, so it would be sort of like this. And if that's totally confusing, it might be a good time to review this information. But when we go to smooth, so let's use blue, when we go to smooth this out, it's basically going to sort of, instead of just being a sharp thing like that, it's going to smooth that out, and so it'd be kind of like this. Kind of like that, which is pretty much like this. I think in reality this might be a little steeper, but whatever. So the velocity graph looks something like that. Notice how her velocity starts off at 0 and speeds up in the negative direction. So this point right here would be where the bungee loses its slack and it starts to tighten up. She's still going in the negative direction. This right here would be at the bottom of her path. So she goes boing, 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 okay? And so right down here at the bottom of her path before she starts moving upward, that would be right there. This would be where the bungee's still pulling and pulling and pulling, and right when the bungee stops pulling, okay, and then it's gravity slowing her down and slowing her down, slowing her down as she's sort of in this free fall moving upward. And then this would be at the top of her path, and then gravity's pulling her down, pulling her down, pulling her down, pulling her down, and right as the velocity stops increasing in the negative direction would be when the bungee goes tight and starts slowing her down. Okay. Let's take a look at page 2. Actually, we're at 13 minutes, so I'm going to stop and make part 2 for page 2.